The first talk we have Hélène Esnault, and she will tell us about algebraic flat connection and O-Minimality.
And not much of minimality because I don't know much, but it's a nice chair promise to write a proof here, so it's okay. So first I want to thank the organizers for the very kind invitation, which becomes more and more difficult to honor in our days, but I'm really glad to be here, so thank you very much. And the second thing is I unfortunately have to warn you, I had a high, for my state of mind, I had a high fever the last 2 days. Today is better, but this morning I started bleeding from the nose. So I'm not completely, Pierre kindly gave me a bicycle to go back and forth, but I even left the bicycle at the hotel because I feel a little bit dizzy. So if I say complete nonsense, it's due to my normal state of mind, but my health situation doesn't improve. I'm not going to be able to correct, so I hope I don't make a big mistake. So the topic here starts with yesterday we had a beautiful lecture by Ben, anchored in algebraic geometry, complex algebraic geometry, complex Hodge theory, I apologize. And one of the main theorems, the one which is a bit older, is that the image of the period map in complex Hodge theory is algebraic. It's of course an essential theorem, and the method was O-Minimality. And there is another essential theorem about algebraicity anchored in complex Hodge theory, which was not mentioned at all yesterday. That's a theorem of Catani, Deligne, Kaplan on the Hodge locus. So let me write this, and I can tell you the plan of the talk in case I collapse before the end, is that I'm going to write down the theorem, which is an old conjecture and which has been proven about 20 years or 30 years ago. And then I'm going to do like Daniel did yesterday. I'm going to declare that this is the abelian theory, whatever that means, and go to the non-abelian case, whatever that means, and formulate the conjecture of Simpson, which is analog to this conjecture here. And here I will just list the main points of the proof, and I will raise the question, what happens on the non-abelian side? And I will not touch two of those points, but I will mention them, and in particular one which concerns really Pierre, because even though he was using another language, this was his conjecture before Simpson, and then I will focus on the point which has to do with O-Minimality, and then I will raise one or two questions, and that's it. And I will also give a counterexample to a philosophy which has been spread out, notably by a certain number of people who are here. So, so what is a Hodge locus here? The data are S is smooth, quasi-projective over C. And by the way, if you cannot read, like it was my case yesterday on the board, you just stop me immediately. I will try to improve the situation. And the next piece of data, this is V, which consists of a local system. And then it's the RAM object. So this is an algebraic bundle. And this is an algebraic connection. And then we assume that it is a Z polarized variation of Hodge structure. So I apologize for the acronym here. I hate acronyms. And then so we have a polarization here, and we have an F iteration. Okay. And now one considers, so the first thing people do in order to formulate the old conjecture is that they consider the underlying algebraic bundle as a variety over S. Why not? And then they consider in it the Hodge locus. So what is a Hodge locus? So now this is a section. That's a section Xi, which is a Hodge cycle. And which is defined as. Is that okay? And then the old conjecture is that this locus here, the connected component, are algebraic, and so are the images in S. And this has been solved by Catani de Link-Kaplan. And now as promised, let me say the light pattern of the proof. Viewed a little bit differently than the way they wrote at the time, influenced by your conference, in some sense, the spirit of the conference. The first point is due to Schmidt and stipulates that the F iteration, we can think now of the F iteration inside of V as a variety. The F iteration here inside of V is algebraic. Why is that? Because there is a log extension of the whole situation at infinity, and all those data are finite, and the log extension is locally split. So that gives the algebraicity. The second point, the topic of the conference, is that if we consider U inside of S analytic, which is a contractible open, we don't need pi1 equals 0, but let's say contractible open, and which is definable, so now you know better than me what it means. Then we can consider on U, because it's contractible, we can consider the set of flat sections. Let us do that. So we have a flat section here with values in the local system viewed inside of the algebraic bundle restricted to this analytic open. And then it is a case that the flat section, so this is flat, this is redundant here because I have written already that it is flat here. Then those flat sections are definable. That's the second point. And the third point is based, yeah, maybe let us write it here. The third point is that we can consider now we fix the C here. We are bounding, rather than looking at connected components here, we bound the norm of the Hodge locus we are considering. So we consider the C is a real number. We consider on U, on such a U as written here, and C, we consider the Xi, the section of V over U, which are in the Hodge locus, which are Hodge. I just write Hodge here. Hodge always includes that it is also integral. And which are bounded by Q. So the norm which we had here, bounded by C, I apologize. And the theorem, in fact, one of the essential theorems is that it is finite. And as a corollary, when so now you can write the corollary. Was like a good idea, I apologize. I apologize. I'm sorry, I can't find it. And the corollary is that if you put 1 plus 2 plus 3 together, then you obtain first that this, because the flat sections are definable, you obtain that so S is covered by finitely many U's as in 2. That means they are contractible, they are definable. So the corollary is that if you define this as being the union over those finitely many U's of HUC, this is definable. But now, maybe I should write like this, I apologize. I apologize here. And now this lies in V. And now this is a complex embedding, which is closed. And now we have, as explained yesterday, Babel, and which is one of your of the magnificent theorem which has been used in all your work. That's the theorem of Peter-Thiel and Stachenko. I don't write it because I will misprint it. That's what is called definable gaga. This implies, so let me just write definable gaga. This implies that HC is algebraic. Okay? So now I do like Daniel. I go to the so-called non-abelian side, and not in absolute generality here, because we, of course, to consider the variation of a structure is not an absolute generality. But here we have absolute general theorems here. So the setup here is as yesterday. So we let me write here non-abelian. So non-abelian means that we vary the scheme. And we replace everything which looks like a Gauss Manin, we replace it by the variation of the moduli. Except that once I've said that, I haven't said which moduli. Daniel yesterday was considering the Durham moduli, the relative Durham moduli, because this is the one which is adapted to the peak curvature conjecture. But a priori, we have at disposal the Betti moduli and the Dolbeault moduli. Before I write, let me just talk. Now, the Betti moduli, as Daniel was explaining, it's constant. It defines the foliation. Why? Because it depends only on the fundamental group, and the fundamental group in our variation. So the data here is X over S is smooth projective. So by the theorem of Erosman, it's a topological fibration. So as a conclusion, the Betti moduli, we have a constant fundamental group, except for the base point. And the moving of the base point gives you this foliation Daniel was talking about yesterday. But essentially, this is constant. And that corresponds, so the Betti moduli here, it corresponds to the flat section. And now earlier on, we had given this variation of a structure here, and we were looking at the underlying algebraic bundle. But here we have at disposal, we have two choices, perhaps. We have the relative Betti moduli, and we have the relative Dolbeault moduli. I mean, this case here doesn't predict exactly which one is better to consider. So we write both on the board here. So what did I want to say? So once I've said that, so now maybe I can write the conjecture of Simpson. In his fantastic article, which contains, I think, like 12 chapters, and each chapter is like a mystery book. He writes very colorful and full of ideas. I don't think even 1/3 of this whole article is completely understood in our days. So he defines in this one here, but he could define also in this one. He could also take the one which moves on A1, which had been introduced by Pierre. But let me write it here on the Durham side. He considers, so he calls it the Noether-Lefschetz locus. I don't like this terminology. I will also call it the Hodge locus. And just to say where we are, we put the Durham here. And this Hodge locus, consider, in fact, I didn't say what are the complex points of this relative moduli. So it's, I didn't say which moduli I consider. I consider the coarse moduli, but I could consider the stack. It doesn't really matter. So if I consider the coarse moduli here, a complex point, what is that? It's first a fiber. I mean, it's a point in the base. And then on the fiber, it is a semi-simple Durham object connection. And here you would have the same description. A complex point would be a point in the base and in the fiber, a semi-simple Dolbeau object. Of a given rank, of course, we fix the rank and so forth. And so then the Hodge, we look at it inside here, it's a locus. And we are looking here inside at the Z variation of our structure, polarized variation of our structures. On some, I denote the fibers by X lower S here. So it's a locus. It's analytic. And it has infinitely many components, so we can look at connected components. And then the conjecture of Carlos here follows word by word the classical Hodge conjecture here. The conjecture is that any such connected component is algebraic. And so is its image in S. Needless to say, it's a very deep construction. There's no doubt about that. And when we do like Daniel yesterday, we follow the proof here. So I say in word, so that's a problem here. And my talk is not going to be on this because I don't have a really brand new idea to propose on this problem, but I'm going to underline one or two difficulties we encounter on this once we have understood the theorems, really the theorem I want to present. So let me, because as I said, my brain is not functioning completely normally here. So let me say one word before I proceed. We had 1, 2, 3 here. Let me say we understand the analogy of one. In fact, Daniel was talking on the analogy of one yesterday, but there is also another analogy. So let me say one word on this. Even though this is not the topic of our lecture, let me raise a question here on this, and then let me focus here. So I postpone the discussion here. So let me just say here on one, I mean, the analog of one here, that's the analog of the F iteration in its algebraicity. This has been already considered by, what Daniel was exposing yesterday beautifully. This is the content of Simpson's article, one part of Simpson's article. He considers the Dolbeau moduli. He thinks of it as being the analog of the F iteration, and this is purely algebraic. So I don't write it. Now, for this problem here, it is also convenient to change a little bit the viewpoint, not to take this analogy, but to consider above the Durham moduli, to consider a Grassmann of all possible flags in the underlying vector bundle. So we have points here, points are fibers and V common blah. And then inside of V, you can consider the filtration, which is locally split. And in addition, you can put the Griffiths transversality condition on it. So this is still, all that is purely algebraic. And then you can consider in this big Grassmann, and this is not so big because ultimately you have the rank is given, so it cannot be so high. And then inside of, you can look at all the connected components, and ultimately you will look at those components which contain complex variation of structures. And then it will be the case, even though it's not written, that once a component contains a complex variation for structure, in fact, the whole component consists of a complex variation for structure. But that I haven't thought so carefully, so I don't insist on that. But this is another analogy which is adapted to the problem here. Now on 3 here, we know very, very little because it is going to tell us, what we wish here is that if we take a connected component here, and we look at its image on S of the Roche locus, of course, not everywhere. Then you will, if you follow what is written here, then you will suspect that you will prove that it's a finite map. In fact, more finite and étale, but let me just write finite. Now, if you look at that, you come again into the mathematics of Pierre Deligne, because he proved that if S consists just of spec C, if there is only one point, that is precisely his theorem here. He proved that there are only finitely many Z variations of Earth structure on a scheme. In fact, the scheme doesn't even have to be reduced or smooth, doesn't matter. You have only finitely many Z variation of Earth structures. When you fix, you fix the algebraic structure of your underlying topological space to be able to talk on Z variation of structure. If you talk only on the local system, of course, it's a topological statement. And the statement is not so well written because you have only finitely many, his theorem, you have only finitely many low Z local systems defined over Z, which underline polarizable variation for structure, but that's the same theorem as the one I said, ultimately. So, and he raised this already in his article. By the way, his article was written after Faltings proved you have only finitely abelian varieties with given degeneration. He wanted to understand the analogy on the Roche side, and this is the result. So it has many ramifications like this. And then he raises already the question, what happens now if, for example, I am on a curve and I change the complex structure? I have the topological curve and I change the complex structure. Is that still the case that I have only finitely many such? That would be this question here. And on this, we have already a beautiful result by Engel, Philippe Engel and Salim Tayou. Under some very, very, very strong assumptions, they managed to prove the finiteness here. But in fact, Salim was telling me that then they generalized, and at the end, they had to throw away all they had done because it was a mistake. And yesterday, Daniel, we had breakfast together, and he was explaining to me that then he talked with Philippe, and they had a proof, and again, there was a mistake, seems to be very hard, and who knows, maybe not true, or we don't know. But at any rate, it's a question here. So now it's not the place where I am. So now I come to 2 here. And I don't discuss on 2 immediately, but I have to recall the definability. And this is not the place for me to do it. Because surely I would say something wrong and it's not good. But for me, so now I come back, maybe I should say where I am here in the logic of the talk here. I go again to the so-called abelian side here. So that means I have just a V over S here. And so we have, this is an algebraic structure here. This is an algebraic structure. And when we say that, when we start with Z variation of hot structures and the flat sections are definable, so we have to understand definable, and this is too difficult for me, but at any rate, I can say one thing, and this is the only thing I'm going to use, is that definable functions here do not oscillate. So on the opens on which they are going to be defined. So that means that we have plenty of properties. They are a little bit over-convergent, and they might be algebraic, real algebraic, real analytic, real exponential, or small enough opens, but large enough in some sense. But the thing is that you cannot have sign, for example, or you cannot have a periodic. They do not oscillate, and there is no periodicity. And so this is all I say here. And now I am in the position to give a general, because you have two here, but two concerns the Z variation of a structure. So you may raise the question, what happens, and I don't have to write here first. There's one, in order to motivate what I say now, let me say here for Simpson, because he proved all that, when S is proper itself, projective, let's say, then he proved his conjecture. Because of Gaga, classical Gaga. So, so it was just a remark. So now if we look at this general problem here, so we will have a V like this, but it comes from a V nabla. It's just an algebraic connection, as we had at the very beginning. So now it makes sense to ask, when is it the case that the flat sections on definable opens are definable? In view of this program in quotation mark here, in particular this non-abelian part, you can ask in general, when is it the case that flat sections are definable? And it always means undefinable opens, blah, blah. Flat sections are definable. And always on U, as we had before, and with values in the local system, but inside of this algebraic structure. And this is precisely the theorem of Ben and Mullane, or one part of the theorem. Then it shows that if the connection here, so maybe we have a name here, this algebraic connection here. When I say connection, I always mean integrable connection, of course, I apologize. So if nabla is definable, so he doesn't answer my question, he answers the other question. If it is definable, what algebraic property we have? And of course, let me insist again, if S was projective, then every flat section would be definable, right? But so it's a condition at infinity. And their answer is, if it is definable, it implies two things. The first thing is that at the boundary, nabla is 10, is regular singular. But it's not enough because we had already the theorem which is in selection notes of the line. What are the solutions of a regular singular connection at infinity? Those Nielsen class function, etc. But if it is definable, it implies more. And what more? It's a sort of a compact story. This non-oscillation here will imply that the eigenvalue of the monodromy at infinity have absolute value 1. So it's a very enlightening theorem, which does not quite answer my question, but which gives a way to think of it. And now we can answer the question. So this is a work I started with Moritz. So it's not over, so it's ongoing, but this part is understood. And in fact, you can also look at it, for example, on the webpage of the volume for Gérard Lomont, who passed away now like 2 weeks ago. And then the theorem is that it's if and only if. So let me comment here before going on. First, let me say there's one way to comment and another way to comment. The first way to comment.
So in your converse, the definable is exactly analytic, as you said, with exponential, right?
This is always with exponential, yeah, because already when you don't have any poles.
I'm just
thank you very much for the question. So I think you have those beautiful take.
All right.
Better, huh? Okay, so it's you have two philosophically that gives you two ways to think of this. This is an algebraic statement here. Why is that algebraic? Of course, to be regular singular, if you take the initial definition, I apologize, basically of the 19th century, it's a gross condition at infinity, so this is analysis. You can say more precisely, it's asymptotic, an asymptotic of solutions. So it's analysis, asymptotic analysis of the flat sections. And that is something very specific, which I cannot say. But I can also say, so I can say this is asymptotic analysis. Because we are also going to recognize the second condition on those. But you can also say this is algebraic. You can also say that. But what is written here, the definability, this is really analysis. Those are on functions. So here, this is analysis. Let me make another remark. So this is one way to think. Yeah, sure.
So if you write down the algebraic differential equation on the affine line where the solution is the exponential function, so you're just saying that doesn't count as definable?
It depends on the eigenvalues at infinity.
Irregular. It's irregular. So what, can you say something about what definable means that rules that example out?
No, yeah, maybe you answer. I don't want to answer on definability. I can tell you what I understand, but yeah.
I mean, so like it'll be definable like in restriction to like a fundamental domain, basically is what's happening in that case. So like the exponential restricted to a bounded vertical strip is sort of what happens there.
Maybe the answer is like the convex exponential can be definable because the preimages are countably infinite. And definable means every like discrete that you can define is finite in particular. And so e to the z can never be defined. In this case, the connection is not regular, is what fit to the theorem.
So nabla definable, it's not about nabla, it's about the solutions to nabla.
Yeah, I think I know here is talking about the solutions, right? When you say definable.
Also, I think the arrows might be.
Yeah, I'm also a bit confused about your arrows.
Yeah. The way you have it,
No, these arrows are like this, I have.
that's why I was asking you.
Thank you very much.
I was asking you precisely because you were going to conclude it's
Thank you,
definable.
thank you. Yeah, thank you very much. Thank you.
It's the fever.
It's not fever, it's the. Thank you very much. Yeah. So, and the second remark I want to make before proceeding is that one way to think is that this side here, which I said is algebraic. Why is that algebraic? Because of this log characterization. And also those two conditions are conditions which are formal at infinity. It's purely, there's no analysis. So this is formal. But here it's not. Okay? So thank you very much for correcting me.
So eigenvalues of absolute value 1, that's a period weaker than saying that the actual monodromy group is unitary.
It says it's an extension of such. And that's a monodromy at infinity. When you say that the eigenvalues of the monodromy at infinity are 1, the eigenvalues, the absolute value of the eigenvalues of the monodromy at infinity are all equals to 1. It's just saying that when you look at the successive extension of your monodromy at infinity.
No, but I'm asking about the global monodromy.
No, we talk only on that's monodromy at infinity.
So, okay, so there's no statement about the global monodromy after 10 years, right?
No, it's a look,
Okay.
you can, it's a monodromy at infinity. Eigenvalues of the monodromy. And as I tried to say before, when you are on when S is proper itself, there's no issue. Everything is definable. So let me now postpone the sketch of the. In fact, I should pay attention. When did I start here? Well, it's not much time. So let me maybe we do with philosophy here. Let me once I have written this. Let me come back to this dreamed program, non-abelian program, just as a philosophy. And as I said, one is understood in several versions. We don't know which one can be useful, but 3 is very hard. We don't know. Maybe it's wrong, maybe not. And two was that the flat sections here are definable in the abelian Hodge problem here. So you can say, because you say the analog of V is, at least in the lecture yesterday, the analog of V was a Durham moduli. And by our discussion before, the Betty is at the flat sections. So that means we are looking precisely at what Daniel and everybody calls the isomonodromic deformation of a given local system on a given fiber. So you are looking at the section. So you have here, let's say, a sector U, and you look at the inside of M Durham X of S. You look at the isomonodromic section defined by the initial condition, and the initial condition is precisely the Durham object you have on one fiber. So define by nabla on one fiber. So you could wish that it's definable. Now, all this, and it is already in Simpson. I just repeat what people did before. Simpson, so now let us step back. Because you would wish this under the assumption that this moduli here, which is defined purely algebraically. Let us record here that this moduli is associated to any S-scheme you consider the connections on Xt, the pullback. I mean, relative connections, relative. And then if it's not the stack, let's say semi-simple for simplicity. So that, and now, I mean, to make sense of this problem here, it is, otherwise you don't prove anything because this is precisely the moduli you're interested in. It's not something else for Simpson's conjecture. And if you start talking on definability, then what you wish is the analog for in the definable category. What you wish is that those moduli here in the definable category come from the algebraic moduli. So that means what you wish is, let me say more precisely, you have the theorem of Simpson, again, which is telling you that in our situation, so this is always X over S smooth projective here. So he's considering this algebraic moduli, which is a solution to this moduli problem. And then he's considering another moduli problem, which would be here an analog in the definable category, but he does it in the analytic category. He's considering the moduli problem. He looks at an analytic T over S, and then considers, he assigns to this the connections on Xt. But now you have only analytic connections. And what is the answer of Simpson to this problem? He says that, let me call it, he says that if you look at this algebraic moduli here, which is an answer to this problem here for algebraic maps, and you look at its analytification, then this is precisely this analytic moduli. So this is, of course, so now if you go to the definable category, it makes no sense to look at definable objects, whatever, if that is not true. I mean, but on the other hand, I mean, everything I'm talking about here is really John work with Moritz. I should really, I wrote it already, but I should write it again on the board. And this is really in the making here, so in progress. So on the other hand here, I claim that this is not true. So the analog best change statement here in the definable category is not true. So analog best change statement. And this is easy to see. For example, take S to be GM, and take your family to be a constant elliptic curve. And now look at, so you are looking at, you can take the topology, I just do the line bundles here, I don't do connections. So take your elliptic curve, you can cover it by two opens, big opens, which are definable, and the intersection is a disjunct union of two opens, each of which is homotopic to S1. So you can take a trivial rank one bundle on the first big open trivial rank 1 model, on the second big open, you can make the trivial gluing on the first intersection and make a second gluing on the second intersection, which is not trivial and which moves completely, which is just multiplication by GM on the transition functions. So that gives you a moving definable bundle. And so that gives you a map here, which because of Gaga definable would be algebraic from E to peak E cross GN. That would be algebraic, but it's moving in the elliptic curve. So when you project it to peak E here, if it was algebraic, it would be constant. Okay, so when you go back in time here, the thing which doesn't seem to be true now, that is a guarantee. But the next thing is the way one constructs moduli here is, for example, with a quote construction of Grothendieck. And the key point, as explained by Simpson when he does his proof here that you have best change in the analytic category, the key point, all the rest goes through in the definable category, but the key point is Crowert coherence theorem, that when you have a proper algebraic morphism, morphism is algebraic, the push down of a coherent sheaf is coherent, and this is what should break down here. So, and interestingly, Ben Jacob and Johan, they had definable Crowert theorem here, but for a projective map, they were more or less asking in general. Okay, so I come back to, how much time do I have here? So I come back now to the proof here. So, as I said, we are comparing an analytic condition and a formal condition. And now we are in the situation where we have the formal condition. And the way to compare the two is, so maybe I should start, let's say, main points of the proof here. So the main point of the proof is the first point is that when we look at what I call the algebraic or formal side here, you may assume, because of the curve criterion for tameness of connection, and the curve criterion to understand the eigenvalues of the monodromy at infinity, you may assume that the base is one-dimensional. And in addition, it is also true because you are looking at small opens, not completely small because you want your base to be covered by finitely many of those, but nonetheless, small enough, essentially, you may assume that your base is delta star. And then in addition, all those notions here are compatible also with ramification. So now if I want to compare this formal side and formal formulation and analytic in quotation mark of formulation, I have to replace the formal side. So let me write here first formal and later on analytic, but not completely analytic. So I write analytic in quotation mark, but let me write first the formal side. Then we know that now I need my notes here. So we know that when we have a differential equation here on the puncture disk here, which is written as z y prime, so that's the solution here, equals a of z y, where, so now I write here, where A is written. I do a level here, but I do it the way Moritz like, and that makes me completely expressive because I never managed to write the correct thing here. So it's a diagonal matrix Qi of the identity plus Bi. So this is a constant matrix. And the Qi here, that's the whole salt here. This is a homotety for the identity matrix here. And this lies is in 1 over z, c 1 over z. And then the differential equation is written here. And then Mullane is telling us that the solution are given by, let me write curly y here. Diagonal of, so I should write here z to the power bi, that's a matrix, and then exponential of integration qi of z divided by z, maybe dz. So that's Turing level. But at any rate, well, I don't like this way of writing things, but this is equivalent, and this is the way one needs here. And regular singular here, which is what we want to achieve, as Ben was saying, in that direction. Regular singular is equivalent to saying that the Qi are 0. And then the eigenvalues, the absolute value of the eigenvalues at infinity are 1. This is equivalent to saying that the eigenvalues of Vi are in R. I think that's the condition. And then I'm done with the talk. Then then you just write. So that is a formal solution. That's a theorem of Turing level. And now the way we formulated things is by using what is written in the literature as asymptotic lift. Of those formal solution. And now the keyword here, those asymptotic lift here, they are analytic in some sense. And the key word here is that those asymptotic lift are multi-summable functions. As multi-summable functions. So I'm really not a big specialist of this formulation here, but this formulation here is beautifully explained in a volume by Van der Poot and Zinger. The notion itself, as we could understand, comes back to Ekal. So another way for the same reality, mathematical reality here, that's Ekal functions here. So I don't know what exactly. But the bottom line is that we are on delta star, and then there are finitely many rays here. Which are excluded from the discussion, but part of the definition here is that they exist. The important word here is that there are finitely many of those, which are such that if I consider any other ray, so I should not take color because yesterday I could not read the color, but I just take any ray here. So let's say tau for a ray. Then in a sector, along tau, and a sector with angles which go smaller and smaller, then we can write after ramification of delta. We can write the solution as a sum of solution, as a sum of functions in sectors which are smaller and smaller, which have the property that they have an analytic expansion. With a strong condition that the coefficient of this analytic expansion here, they have a strong convergence. When we look at the coefficient and their absolute value, they define for us a value in zero of this expansion. Of course, it's not analytic, but it's defined. So we can define the value in zero. So I'm very vague here. But the point is, due to those people here, and maybe earlier, that when we have a formal solution here, then there exists a multi-summable lift of the solution, which is called in the literature asymptotic lift. And so this means that this solution we had, which was formal, lifts two. And now let me write here Z. Z of, Z of Z is maybe not so, let me write a double Y like that. Now it's on the sector here, so this is multi-summable. No, let me write here. We have the same diagonal term. Because the diagonal term here, you know, you had finitely many poles and you had constant matrices that don't perturbate the analysis. But you lift the coefficients which you had here, you had no coefficients, so one, you lifted it to functions here, around, so on the sector around tau. You lift to a function here, and this function is multi-summable. And the condition is that when we look, let us make an example, and in fact everything reduces to this case. Let us reduce further the problem to rank 1 differential equation. Then when we do that, what we have written here, and now I really need my notes here. So we have this Q here, which we had the term which appears in the exponential. So we have Q, which is, let me write here, QK Z minus K plus etc. Q1 Z minus 1. And then we have a B in C, because we have rank 1, so we have the constant coefficient which is here. And we want that the function here, which are assigned to Z on this sector, the exponential, so now I just write here. So this is the assumption. Once I have written the assumption on the correct side, the assumption is that the exponential of I times imaginary part of phi of Z plus B of Z, this is definable. So that's the assumption. And now this is telling us that, except that I made a mistake here, this is Q. This is telling us that on this sector, so this is telling us that Q of the sector lies in R and B lies in R. So we have already the condition on the eigenvalues at infinity. And the fact that Q of a sector lies in R implies that Q is 0. Okay, so that's this is more or less the spirit of the stuff here. So I apologize for the painful discussion here, but it's maybe not so important, but the philosophy which is behind is maybe more important, and I thank you very much for your attention.
Thank you. Any questions for Hélène?
Sure.
So I guess if you want to understand M-DRAM, maybe it makes sense to ask affiliation, what conditions do you need to place on it to make the leads definable in our
Yeah.
Yes.
Okay, so I haven't talked on this. In fact, I more or less thought very early this morning I should, but I haven't. I apologize. But there's one thing. So let us maybe forget this. But let us come back to the salty part, which is behind why do we do that? I mean, that was a motivation. So as now we come back to, is it the case that when we look at M-DRAM and we look at isomonodromic sections, they are definable yes or no. And for this to be sustainable, so to speak, as a question, we would need that M-DRAM has the property of Simpson, but it has not. But so before I go to your question, because I don't have an answer, let me try to bypass your question and go differently. Our thought was, and I don't know whether Bruno is here. Maybe he's not here, but Bruno had, yeah, let me write. Our thought was that maybe what is true is that if we look at the isomonodromic section, but now not in M-DRAM, but in M-Dolbeau, of X over S, this one would be definable. That would solve the problem, not as you said, because here we will not be able to apply any definable Gaga because it's not complex analytic. The underlying algebraic structure change, it's real analytic. So there would not be any contradiction with what I explained before. And it would enable one under the assumptions that the finiteness 0.3 is true, that would enable to close the program. So that's the way we think. And I should say that in that direction, there is a work of Biswas and two Hellers, where he computes precisely this in a different language for in two cases. The first one are for the unitary connections. So this is, of course, he doesn't present, of course, the thing in this language. He says, I fix a monodromy representation, and then I look at the section it gives on the Dolbeau side in a family of curves. And then he asks when this locus he defines like this, which in our language here means isomonodromic section associated to a given object, but on the Dolbeau side. And then he asks when it is a case that it is algebraic. And then he has two cases where I can conclude. One is unitary in general in any rank, in any dimension, I apologize, and also in any rank. And the other one is for SL2 local system. Then he concludes that this is true for unitary ones. And he also has a remark that in higher rank, you have more than unitary ones. He singles out one example which has this property. So it's not completely, that would bypass the question precisely you say. Now, of course, this defeat, so to speak, with this example I was giving, a counter example to your question, more or less. This defeat, this doesn't say that when we look at the iso-monodromic representation, which is which initial condition, which is really a Z variation of a structure. Maybe more is true than what I said. I'm not saying this, but the program then needs a fix. Yeah, so it's not exactly, so the second part is part of your question, not the first part, but the first part would be a general fix here.
Okay, other questions? I had a small question
Of course.
about this proof. So, I mean, it seems to me that what you really need, so do you really need this multi-summability theory, or is it enough for you to know that there is a solution with, so say you have an irregular singularity, so you know that there should be formal solutions that look like, well, exponential times some power series, which is actually multi-summable. But do you even need to know that it's multi-summable? Wouldn't it be enough for you to know that there is an actual solution, which is asymptotic to, let's say, e to the z times 1 plus little of z, because I think this should be easier. There is I mean, multi-summability really says that, you know, in sectors you can reconstruct the function using Borel summation or something.
Exactly.
But just the fact that you have an asymptotic solution for a given formal solution, I think, okay, I would think maybe it's easier. Would this be enough for you, or do you? Or
I cannot tell, because the main point is what is written here. That once you have this condition here, which is coming from the definability, you can conclude this. So that is okay, but you can conclude that Q is 0.
So suppose you knew you have a solution that looks like e to the z times 1 plus O of, you know,
Exactly.
then this would not be definable because the O of 1 over z cannot fix the I mean, you know, z oscillates and O of 1 over z.
There is maybe something, yeah. If I would be glad, because if you could say that by analysis you have one term which is so small that it's not going to perturbate the proof here, then that would be of course better.
Oh, I think one should think about, but it might be short.
Yeah, I would be very glad if you could complete the articles. I mean, the note, it's a note here. Yeah.
Okay, if there are no other questions, then let's